Today we have Eve, who is one of our consultants. She's going to be talking to us about interactions in regression, what they're doing, and how we can try to understand them when they come up in our analyses. For any of you who haven't come to our monthly seminars before or are unaware of what Stats Central is, we are a team of consultants situated in the Mark Wainwright Analytical Center, and we are tasked with supporting researchers in the research design and statistical analysis portions of their research. So we provide complementary services to research staff and faculty anywhere across the university, and also lots of help to HDR students as they go through their theses. So from their design portions all the way through writing it up and responding to reviewers' comments. And we do that as a complimentary service. We also contract with particular schools and units across the university for really sustained help if they want access to our expertise on a weekly basis or so. They can hire one of us for a portion of our time. We also help people get their grant proposals ready if they're going to be submitting a grant to one of the big national schemes or other types of schemes. We're happy to take a look at the quantitative portions of their grant proposals. Also in that support for research in the university, we do some teaching. So we have, right now we just started our short course series. So we're doing some introduction to R courses right now, and coming up we'll be doing some statistics courses, one based in R, one based in SPSS, and those are coming up just in the next couple of weeks. So we welcome you to take a look at our website, and if any of those interest you, you can get a little bit more information on our Eventbrite page. I think that's about all. Eve, are you ready? Happy.
I am.
Okay. Yeah, please welcome Eve and enjoy her talk.
Cool. Hi, everyone. So yeah, let's talk about interactions. So I'm just going to dive right into an example. Right, cool. Let's think about a study. And the study question is there an effect of a particular diet on self-esteem? So I used this one because I found a data set in R. And so the design of this study had enrolled participants into either a control or a treatment diet. And they completed a survey before and after this period when they were on the diet to see if the diet impacts their self-esteem score. So in this study, there's three variables. There's time, which is a categorical variable before or after, treatment, which is either control or the treatment diet, and the outcome variable, which is self-esteem score. So in this study, the interaction is that we're going to talk about is a time by treatment interaction. So we want to see whether the difference in the scores, so after minus before, which is the effect of time, depends on which treatment group they were in. And so an example insight that you might get from this study is that if the interaction was significant, we might conclude that the diet increases self-esteem. Also, we'd want to have a look at the direction of the effect to make that conclusion. And if the interaction is not significant, then we're going to conclude that the treatment group changes are no different to the control group changes. So it could just be some kind of learning effect from completing the self-esteem survey twice that they both get. This is what this study data set looked like. This doesn't tell the full story because there is pairing, but I'm kind of glossing over that to tell this interaction story. So we've got the control group on the left, and it looks like at time 1, T1, at the red box plot, their self-esteem scores were a bit higher maybe than at time 2, although there's a lot of overlap, so that looks like maybe no change. And then in the diet group, it looks like there also looks like no change, but maybe that effect is different to in the treatment group, where in the control group where their self-esteem went down. So what we're looking for is whether the differences between time 1 and 2 is different in the control compared to the diet treatment. So this requires a bit of revision of the linear regression equation. Hopefully there's not a lot of formulas in this talk, but I do want to go through it. When you fit a linear regression with 2 variables and an interaction between them, you're fitting this equation. So you've got an intercept, beta1 is the effect of x1, beta2 is what they call the main effect of x2, and then beta1, 2 is the interaction between them. So, so here, x1 is time, so it's either 0 before or 1 after. X2 is treatment, which is either 0 before or 1 after. And so if we want to know what the average difference in self-esteem score is in the control group, we just look at beta1, because in the control group, x2 is 0. And so this term here and this term here, they cancel out because they've got zeros in them. And so the difference between the control group, the before and after, is going to be beta1, because it'll be beta0 plus beta1 minus beta0. If we want to know what the average difference in self-esteem score is in the treatment group, then we have x2 in there as well. And so then we're looking at x2 is 1. And so we're looking at beta0 plus beta1 plus beta2 plus beta1, 2 minus beta2 minus beta0. And so that's the average difference in the treatment group. And so what you can see here is that this beta1, 2, the interaction term, it is the difference between the control group and the treatment group, the difference between their differences. And so if we look at whether the treatment is significantly different to the control in its effect on self-esteem scores, that's equivalent to testing whether beta1, 2 is significantly different to 0. I'm going to go through more examples of this and some more different possibilities. If anyone has any questions along the way, feel free to ask as well. So my second example is similar to that one in that it's two categorical variables interacting. And I use this bike rental demand data set for the rest of the talk. That's why all the songs were bikes, which bike related, which someone did notice. So good pickup. In this data set, the variables are like the daily count of bike rentals. So it's like the bikes that you can just rent off the street. And in the data set, people are classified as either a registered user who's renting the bike or a casual user. And so the question that we're asking with this data set is the bike rental demand different on weekends versus weekdays? And how does that depend on the user type, the registered versus the casual users? So here we've got three variables: the daily count of the number of rentals, the user type, which is a categorical variable, and the weekdays versus weekends, which is also a categorical variable. It takes, that's like, yeah. So here's what the data looks like plotted out as box plots. On the y-axis is you've got the count of bike rentals, and we've got the casual users here, and they seem to use the bikes more on weekends. So sorry, the red box plots are weekends and the blue box plots are the weekdays, because weekday is one. But they overall use the bikes less than the registered users. And then if we look at the registered users, it seems like they use the bikes more on the on the weekdays than the weekends. But on every day, they're using it more than the casual users. So if we wanted to predict demand on a particular day, it's going to be really useful to split it out by user type. So I would, so this is an example of a linear model for bike rental demand with an interaction between user type and weekday. So if you don't use R, I've tried to not include much of the code, but when I upload the slides, the more of the code will be there if you want to see it. But the main thing I want you to take home is an idea about whether you need the interaction and how you're going to present the results, not so much the software to do it. So in this example, if you fit this linear model with user type and weekday, you get these coefficients coming out. And so now we're going to do that maths that we did on the other one, but with the results of this model. I did take the log, so we're just working on the log scale. So if we wanted to calculate the count from registered users on a weekday, how do we get that from the outputs of this model? So we're going to take the intercept and we're going with registered users. So user type registered is included in this in this sum, because that's the x1 variable that equals 1. And we're looking on weekdays. So weekday is 1. So we subtract 0.8 and then we add 0.11. I'm not sure why I didn't calculate these. I just left them as sums. And so for each of these statements, we just need to pick out the relevant coefficients to get the answer. So if you want the expected count from registered users on the weekend, you still have the intercept. You also have the registered users, but you don't have these two terms because they're equal to, weekday is equal to 0. So these terms only come in if you're looking on a weekday. Now, if you want to look at the expected count from casual users on weekdays, you take the intercept, 6.9. Now, user type is not registered, so this term is not in there. It is a weekday, so we get the minus 0.8, and we don't get this term because user type is not registered. And casual users on the weekend is the intercept. All the other terms are 0. So, so that's how to calculate the estimates in each subgroup from those linear model coefficients, the way that it will come out from the software. But plotting confidence intervals is a good way to visualize results. So these are confidence intervals for the estimated number of users in each group on each particular day. And so these confidence intervals, I just use software to calculate them, but each estimate is actually the sum of coefficients. So it doesn't generally come out from a summary table, and you have to use the variance covariance matrix to calculate the standard errors of each estimate, which is the sum of coefficients. Anyway, don't worry too much about that. And here you can see definitely looking like that interaction was significant. And if we used summary to have a look at the significance of each term, you can see that the interaction was significantly different to 0. It's got a very small p-value. So that's if you wanted to do a hypothesis test for do demand patterns depend on user types. So a few points here. It doesn't make much sense to talk about main effects in the presence of significant interactions, because the significant interaction means that the difference between weekdays and weekends depends on the user group. So you can't say overall demand is, people demand bike rentals more on the weekend because in some user groups they don't. I guess there are contexts where you can interpret main effects, but in general, the interaction means that the difference depends on the user group. We don't tend to care about whether the main effects are significant or insignificant if the interaction is significant. But one thing we might care about is which levels of one of the variables, like user type, the effect of the other variable, like weekdays, is different to 0. So we might want to estimate the differences between levels of X1, conditional on the levels of X2. So if that sounded a bit confusing, by that I mean looking within casual users, let's estimate the difference between weekdays and weekends. And we find that the difference is, this is on the log scale, 0.8. So more on the weekends, and that's significant. And then looking in the registered users, the difference is minus 0.3, and that was also significant. So sometimes you might find a significant interaction and you have a categorical treatment variable and some other groups, types of your in your sample, and so you can look within each type, did you get the treatment effect or not, and things like that. So so now scenario 2, so what I just talked through then was interacting a categorical variable with a categorical variable. I'm going to look in the same data set, but I found another variable called that was temperature. And so looking at what an interaction between a categorical variable and a continuous variable looks like. So to talk through the data set, bike share rentals are affected by temperature. And this data set's from somewhere cold in America. I've forgotten the city. So in this data set, it seems like the warmer the day, almost the more people rent bikes out. But the relationship between temperature and bike renting might depend on the user type. So the question that I'm asking is, what's the association between temperature and the rate of hire for each user type? And do the user types have different associations with temperature? So here the variables are count of bike hires, temperature, and user type. And so we're fitting a model with an interaction between user type and temperature. Temperature has been scaled. So here's what the data looks like. The registered users obviously rent bikes more than the casual users. That's why the blue dots are mainly higher than the red dots. And then it looks like both of them like to rent bikes a bit more when it's warmer. And it looks plausible that the casual users have a steeper slope than the registered users. So they look like they may be more sensitive to temperature. That means as temperature increases, it changes the way that they rent bikes more, whereas the registered users have a more flat relationship. So if you fitted this model, it's fitted the same way in R, got temperature and user type interacting with a star in the middle. And then most softwares will give you results like this. So an intercept, a slope for temperature, a user type registered addition to the intercept for the registered users, and then this is the difference in slopes between the registered users and the casual users. So the slope for registered users is 3.7 minus 2.1, kind of rounded a bit. So that's 1.6. And the slope for the casual users is just 3.7. So that's what has been plotted on that plot. You can also get confidence intervals for those slopes within each user type. So if that was part of your study question, you can estimate the trend 3.7 and the confidence intervals from 3.47 to 3.97 and 1.66. And here's a confidence interval for the slope with registered users. So the kind of conclusion, and so the other way that you could analyze this interaction, if you were asking a hypothesis, if you had a hypothesis, was that, if you were asking, is the way demand depends on weather different for different user types? That's like testing whether the interaction term, the difference between the slopes, is different to 0. And so using summary in R, you can test whether the interaction is significantly different to 0, and it is. And so that's saying that those slopes are significantly different. And this is just plotting it out. Darn it. The slides have run off a little bit. I'll have to fix that before they get uploaded. So the main conclusion from this study is that temperature is significantly associated with higher rates of both types of users, but registered, because they were both of them had confidence intervals that were away from 0, but registered users are less sensitive in that they have a flatter slope, and that the difference is significant to the casual users. Okay, so I did go a little bit gung-ho with these slides. I'm not sure if I'm going to get through them all, but I'm at least going to get through this next example, which is what if bike share rentals are affected by temperature, but the relationship is nonlinear? So I thought I'd go into a slightly more complicated interaction example where the results are harder to interpret. So the residual plots from the previous model didn't look great. I didn't show them to you, but there was a bit of a trend in them. So the linear relationship might not have been appropriate. So we could fit a polynomial trend through temperature with one trend for each user group. So that might look something like this, where you've got a curvy relationship with temperature, and it's like a different curvy relationship for each user group. So what would that look like in a model? That would basically be like fitting an interaction between the second order temperature term, so temperature squared. The square is meant to be on temperature. Okay, I've stuffed up the slide, but between the second order temperature term and user type. So if we fit that interaction between temperature squared and user type, that equates to us thinking that the shape of the trend is going to be different. If you think the shape of the trend is going to be similar, but the location will be different, you could fit a smaller model that just has temperature and user type interacting, but it doesn't have temperature squared and user type interacting. So, so this model in R, if you're familiar with R code, is just a polynomial in temperature of degree 2 interacting with user type. And this is what the results will look like. And so it's much harder to interpret these results. This is just the fitted model without any standard errors and stuff. But even if we did summary and looked at whether these terms are significant, it's going to be hard to figure out what it's telling us. So I think I didn't do a summary. So I looked at the confidence intervals of each coefficient, and I can see that each coefficient is significantly different to 0. The confidence intervals are away from 0. So they're all doing something, but I still don't really know what the results are telling me. And it's going to be hard to write a statement in my results about what's the difference between the user types and how they respond to temperature. So a plot's a good idea here. So this is just plotting out the fitted model. Here we have the casual users, and here we have the registered users. And this is their predicted counts per day. And so from this plot, I think the best way to go from this to results is just to interpret it like descriptively. And so I've said here that both users prefer moderate, intermediate temperatures. So that means that this quadratic polynomial seems to peak somewhere in the middle, maybe around 0.72. So you could calculate that exact maxima of the polynomial. But the casual users are more sensitive to temperature than the registered users, because this polynomial curve is steeper. And you can actually see that in the coefficients because it's got a larger negative coefficient on the quadratic term. So these seminars are meant to be half an hour, and I'm pretty much there. So my last example was just interacting two continuous variables. And so, you know, it was a bit hard to do that with this data set. So sorry if I'm getting a little bit off the realms of plausibility, but I'm asking, like, what if the bike rental demand depends on both how warm it is and how wet it is? Because there was a variable in the data set called humidity. And so here we just look at the count of registered users hiring bikes to keep it simple. And so here I've got temperature and humidity, and the dark green dots are where lots of people hired bikes, and the yellow is where there were fewer people hiring bikes. And so when we model an interaction between humidity and temperature, both continuous variables, we're trying to fit a 3D surface through these counts as the z-axis. When you try to put that 3D surface in, it's quite restrictive just to add x1 and x2 without adding the second order terms x1 squared and x2 squared. So adding the quadratic terms in as well as the interaction should be your default. So you can do that by fitting a polynomial through temperature, humidity, squared. So that'll fit all the second order terms in R. Or you can do it in other ways as well. And so what it does is it fits a term for temperature, a term for temperature squared, a term for humidity, a term for humidity squared here, and the interaction between temperature and humidity. As you can see here, the interaction is not significant here, which is telling me that the relationship between temperature doesn't have any dependency on how humid it is. And if we visualize the trends, we could plot out the slope of temperature for different levels of humidity. And here, these slopes are all very similar. And because we know that that interaction was not significant, we know that these slopes are not significantly different to each other. Yeah. So just to wrap up, what do you do if an interaction in your model is not significant, like the temperature and humidity one? You probably included it because it made sense in theory. If you refit the model without the interaction, the p-values and the standard errors that you get will be wrong, because that's doing inference after model selection, which is a big no-no. So the advice is to keep the interaction in there. And the only caveat to this is that I do think there are settings where you've got a justification to re-specify the model, but these would be predictive modeling, model selection settings, and not hypothesis testing estimation settings. Just in case you're thinking, but my data is different, everything I did here was a linear model. All of this conceptually extends to generalized linear models and random effects. And if you have more terms in your model, the interaction is still interpreted in the same way. It's just that you've got something else that you're adjusting for as well. And if you want to talk about higher order interactions, like three-way interactions, yeah, that's sort of beyond the scope of this talk, but sometimes a study does call for higher order interactions, but results can get very hard to interpret, and they come with a mandatory consumer warning that you do need a lot of data to fit such a model. You don't always need a three-way. Sometimes two-way interactions is what you need. So what a three-way means is that the two-way interaction is different dependent on some third variable. Yeah, I only recommend it if you're very sure it's needed to answer your question and you have sufficient data. And if you're in doubt, just consult a statistician, as always. Thank you. And
thank you, Eve.
Yeah, I'll stop sharing so I can see stuff.
Thanks, everyone. Thank you, Eve, so much for a great talk. There's a couple of questions in the chat. I'm not sure what the first one is actually referring to, because I think it was the specific slide, but maybe I'll read out Irene's. Or do you want to do it yourself?
I am looking at them now. Okay, so okay. Irene's asked, in case we have factor 1 and factor 2, and factor 2 is a random factor. If we're only interested in factor 1, but there is a significant interaction between two factors, what should we do next? So in that case, if your question's asking what I think you're saying, so you're saying the interaction is significant, but I really only care about factor 1. I would look at what the effect of factor 1 was for different levels of factor 2. So if factor 2 is a categorical variable, and you can look at what was the effect of factor 1 in level 1, what was the effect of factor 1 in level 2, with like confidence intervals. So looking at the effect of factor 1 conditional on factor 2, because sometimes the interaction itself is not the interesting thing. It's the effect of factor 1 conditional on factor 2. So I think if factor 2 is continuous, that's harder. But to interpret that interaction, I would pick a couple of values of factor 2, like high and low and medium, say, and look at what the effect of factor 1 is for those values of factor 2. Did that, hope that answered your question, Irene. Great. Any other question?
Yeah, there was a question in there about beta 0 and others related to beta 1. I'm sure it was related to a specific slide. So whoever wrote that question, Z300, that person, if you have maybe you can email one of us and we can answer your question, because it's kind of hard to go back to the slides right now. We're happy to help clarify, but it's kind of hard to do that right now.
It was. When LM in R spits out its coefficients, one of them is the intercept, and then the others are the B1, B2, and the one that I called beta 1, 2. And it's just matching those to a linear model equation. If you send me an email when the slides go up, if you want to talk through it, I'm happy to do that.
Are there any other questions?
Someone asked if there's a reason I used the log count, and that was a skewed variable. I kind of didn't want to, there was, if you look at the residual plots without the transformation, they looked funny. So I log transformed it, as you often have to do for counts. There's lots of questions in the chat that came up. But it looks like that one's answered as well.
I think most of them, except for the last couple, were answered.
So I hope that you understand a bit more about how you might present your results when you've got interactions.
We've got one just in there that somebody just put in.
Right. These are the kinds of questions that I expected, like all of these what ifs, because that often comes up. So what if the factor 1 itself is not significant in the model, but when we added in factor 2, interaction factor 1, and the interaction becomes significant. Having trouble. So if the interaction is, so if you add in, if you've got an interaction between two variables, and then the interaction is significant, you definitely shouldn't ignore the interaction. In terms of how to interpret it, So the effect of factor 1 is going to be different for the different levels of factor 2. So if factor 1 is kind of your variable of interest, you interpret it in each level of factor 2. Is that what the question was? Yeah, it's hard to yeah, and yeah, sometimes sometimes you include the interaction because you have a reason to believe that the effect of one variable depends on another variable, and you may just be they might just be confounders. So you're just including the interaction between x1 and x2, and what you're looking at is x3, some other variable, but these are just terms in the model, and you don't necessarily go and look at their p-values and stuff, because they're just things that you're adjusting for.
Okay, if there aren't any other questions, thank you very much, Eve. I hope everybody found that helpful. Next month in May, we'll be having a bit of a longer seminar, and Gordon will be speaking about research and study design. And so we hope you join us then. Thank you very much.